Hey everyone, welcome to the second Science Saturday with Noah. I hope you all had a great Thanksgiving, and to get with the new holiday spirit, we're going to be covering heat transfer today. Now, I'm going to quickly go over the materials that you're going to need for today's experiment. Don't worry, they're common household items, and if you don't have all of them, you can easily follow along. You're going to need 3 cups that can contain water, some ice cubes, a deck of playing cards, and 2 balls. I'm going to be using tennis balls, but really any sort of ball that you can easily control will suffice. So now, I think it's safe to say that we are officially in the holiday season. That means it's going to start getting a lot colder out here. If you don't bundle yourself up, you're going to lose your body heat pretty quickly. But that begs the question, why do we lose body heat? I mean, of course, everyone knows that hot things will make cold things warmer, and cold things will cool down hot things. But why does that happen? Well, to answer that, we're going to have to actually define what hot and cold really mean. Now, this may surprise you, but cold isn't something that we can measure. There's no property or numerical value that a cold thing will give to a hot thing when cooling it down. In fact, cold is really just the absence of heat. But if that's true, then what's heat? We know that heat will warm stuff up and turn ice into water, but those are just its effects. What is heat at its core? Do you know? Try and figure it out. Really think about this. Ask your parents if you have to. What do you think? What is heat? You ready for the answer? All right, here it is. Heat is really just the vibration of the atoms in your body or any substance. As you get hotter and more heat energy moves into you, the atoms in your body will start vibrating faster and faster. That's what heat is. So you could say that heat is really just a form of kinetic energy, the energy of movement. So now that we know that, we can begin to answer our original question. Why does heat move from hot to cold objects? After all, even though an object may not have less heat energy, cold objects still have some heat. Well, to answer that, we're going to have to cover a science topic called thermodynamics. The term thermodynamics comes from the Greek words therme, meaning heat, and dynamics, meaning force. So really, thermodynamics is just the study of how heat and other energies interact. Now, there are many laws of thermodynamics that describe how heat functions within our world, but today we're just going to be focusing on the second one. The second law of thermodynamics states that entropy will always increase in a system. Entropy can be defined as basically the disorder of something, the chaos. So really, this just means that in any environment, it will always become more and more disordered as time goes on. Now we can see this with a simple deck of playing cards. Take a deck of playing cards, open it up, place them face up, and spread them out. Look at the arrangement. Mine is brand new, so it's in the default arrangement. But you just want to remember that this is the original ordered state of the deck, the order of the cards. Now shuffle it, or mix it up, or throw it in the air like confetti if you're feeling dangerous. Just change the deck in some way. Do something to it that's going to change the arrangement of the cards. Now look at it. The order should have been modified in some way. That means that it became disordered. In other words, there was an increase of entropy as time went on. Now do it again. Just change the deck in any way. It's a bit windy, so this is a little hard for me. Now look at the deck again. The cards should be in an order that's even more different than the original arrangement. And thus it is more disordered. And we could repeat this for as many times as we wanted. And each time that we shuffled the deck, the arrangement would get farther and farther from the original one, meaning that the entropy would just continue to increase. Now, of course, this principle doesn't just apply to a simple deck of playing cards. It can apply to anything. Now, so let's look at it from a point of view that's more relevant to what we'll be tackling today. Let's look at it in terms of kinetic energy. Now, with kinetic energy, being ordered means having more energy concentrated in specific areas, in contrast to disorder, where everything would just be spread out evenly. Take your room, for example. What does it look like when your room is messy and disordered? Basically, all the toys are just going to be strewn all over the place. Stuff is going to be scattered everywhere. It's going to be a mess. Your mom probably wouldn't like that. Now, what if you made it more ordered? You'd have to put everything up where it goes. You have to concentrate things in your closet, pick stuff off the floor and put it in specific areas. That would be increasing order. The same principle applies to kinetic energy. For a system to be ordered, more of the energy would be concentrated in a specific object instead of being just evenly balanced. Let's say you have two balls. One is moving pretty slowly. There's a good, solid, amount of kinetic energy, but nothing crazy. Now let's say a second ball moving much faster hits it from behind. This one has much more kinetic energy than this ball. How's the kinetic energy going to move? Is all the kinetic energy going to leave the ball in front and just move to this ball? No, because that would be an increase in order, which is against the second law of thermodynamics. If all the kinetic energy were to suddenly be transferred from this ball to this ball, it would become much more organized, since all of the energy would be concentrated in a single object. Instead, the second law of thermodynamics states that over time, entropy and disorder will increase. So, when this ball interacts with this ball, disorder will increase in the system by almost balancing the energy between these two objects. This one is going to give some of its kinetic energy to this one, as this one will then speed up and this one will slow down. We can actually see this right now. So for this one, you're going to want to grab your two balls. First, you're going to roll a ball at a pretty normal speed. Then you're going to roll a second ball much faster. See, as they collide, the energy moves between the slower ball and the faster ball. The faster ball distributed some of its energy into the slower ball, equalizing their speed. That increases the disorder in the system. Now imagine that instead of these balls having different kinetic energies, they have different heat energies. Let's say this one was cold, and this one was hot. When these two collided, this one, since it has more heat energy, would transfer energy over to this ball. The disorder and entropy would increase as the energy gets scattered over a larger area and less concentrated. That's why when you go outside, your body will get cold. It's warmer than the air around it, and so in order for entropy to increase, the body has to transfer energy from itself out into the environment. The larger the difference in heat energy between your body and the environment, the quicker this is going to happen, because it's easier for the entropy to increase as the heat difference would be larger. We can show this principle of heat transfer right now with a simple experiment. Grab your 3 bowls from earlier. You're going to fill them with water. One with cold water, one with normal temperature water, room temperature, one with warmer hot water. Then take some ice cubes and place an equal amount of ice cubes in each thing of water. I'm not very good at this, but hopefully you'll do better than me. Now we wait, and we're going to see which one melts the ice cubes the fastest. The cold water, which has the lowest difference in heat with the ice cubes, the lukewarm water, or the hot water, which has the highest difference in heat between the ice cubes. What do you think? What have we learned today? Will the cold water, will the ice cubes melt faster in the cold water because they're closer in temperature to it? Or will they melt faster in the hot water because the difference in heat is much larger, and as such, entropy is going to be it's going to increase much more as the heat moves from the ice to the water.
With boughs of holly, fa la 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 la. 'Tis the season to be jolly, fa la 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 la. Don we now our gay apparel, fa la 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 la. Throw the ancient Yuletide carol, fa la 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 la.
And there we go. The warm water has almost completely melted the ice inside of it. The lukewarm water still has a good way to go, and the ice cubes in the cold water have barely even started melting. It's because, remember, the warm water had the largest difference in heat between it and the ice. As such, entropy would increase much greater as the water transferred its heat into the ice cubes. Second law of thermodynamics states that entropy will always increase in a system, and it's much easier for it to increase with a smaller increment in this one. Our question today was this: why do we lose heat energy when we go outside? Why do we have to put on these sweaters just because our bodies are going to get cold when it interacts with the cold air? And we found the answer. The answer is that thermodynamics dictates that entropy will always increase in a system. And as such, heat is always going to distribute itself between our body and the environment, taking heat away from our body and putting it into the cold air. Well, that brings us to the end of this second Science Saturday with Noah. I had a great time, and I hope you did as well. Make sure to tune in next week for another fun, exciting experiment, this time involving the invigorating science of insulation. Bye!